So if f of 1 equals 1, f prime of 3 equals 3, and f double prime is equal to 4x minus 4, find the constant term. So we're looking for the constant term of the cubic function f of x. So we need the original and we need the constant from the original. Since we are given the second derivative, we can take the antiderivative of that to find which function. If I take the antiderivative of the second derivative, what do I find?
Original function.
Not the original. If I take the derivative of the, sorry, if I take the antiderivative of the second derivative, what does that give me? It gives me the first derivative, because if I'm going back 1, that's going to give me the first derivative. So the first derivative is going to be the antiderivative of this, which was what? What's the antiderivative for x minus 4?
2x squared minus 4x minus c.
You said minus c?
Yeah, minus c or minus 3.
Well,
Sorry.
technically it's plus c first, right? So we get that, we do the antiderivative. Now we're told that f prime of 3 is equal to 3. That means on the derivative function, when x is 3, y is 3. We can use that information to find our constant. So we plug in 3, this 3, in for f prime of x, and then we'll plug in this 3 for all my x's. This will allow me to find my constant term for the first derivative. So then that's going to be, what's 3 squared?
9
Times 2.
18.
Then 4 times 3.
12.
18 minus 12 is,
6.
so then c is going to be equal to,
-3.
so my first derivative is 2x squared minus 4x minus 3. I'm looking for the constant term of my original function. Yes?
I don't know how you got 2x squared for the first derivative.
Because we take the antiderivative of this here. So we apply our power rule, which says that we add 1 to the exponent and then do 1 over the new exponent. Since there's a 4 on the outside, we multiply by 4, and that's how we get 2x squared.
Oh, I forgot you had to separate those.
Remember, you do the antiderivative of each term. Online, you guys got any questions?
No.
Okay, so I have to keep going because again, I'm looking for the constant term of my original function. This right here represents my first derivative. So I have to take the antiderivative again. That's what my hint was about. You have to do it twice. Because now when I take the antiderivative of this function, it's going to give me my original once I take the antiderivative. What's the antiderivative of 2x squared?
2 thirds x cubed minus 2x squared minus 3x plus c.
Okay, I'm going to use a different letter to represent constants so my constants don't get confused. C represented for my first derivative, so I'll use K, a different variable, to represent it for my original function. So now I can actually find my constant, the answer to the question, by using the first piece of information it gave me by plugging in 1 for x and setting it equal to 1. So I'm going to plug in this 1 for f of x, and then I'm going to plug in this 1 for all my x's. And my goal is to solve for k. That's going to end up being 2 thirds minus 2 minus 3, which is
Negative 13 over 3.
negative 13 over 3. So then I'll add 13 over 3 to 1 to get
16 over 3.
16 over 3, which is the constant of my original function, and that is the answer that we're looking for. If I wanted to, I could provide the entire function, but this particular question is only asking me for the constant. So before we start today's lesson, I want you guys to approximate the area under the curve f of x equals the square root of 4 minus x squared using the trapezoidal method with 8 subintervals from 0 to 2. Trapezoidal method is one of the concepts you guys do need to know for this course. That's why we've done so much of it compared to the rectangular method. It was a way for us to find the area underneath the curve. And this is going to lead into what we're going to be doing today for class. So take about 5 minutes to do this. So remember with the trapezoidal rule, okay, there's a formula that's inside of your reference booklet that you can use to help you approximate the area underneath the curve. I believe it was 1/2 h double parenthesis y0 plus y sub n plus 2 times y sub 1 plus y sub 2 plus however many y's, leading to your second to last term. I believe that's the formula that's in your reference booklet. Okay, so this is exactly what you use to determine the area. There was a formula to find the value of h. Does anybody remember that formula from 5-7?
B minus A over N.
B minus A over N, where B and A represent what?
The 0 and the 2.
The 0 and the 2, basically the bounds in which you're trying to find the area underneath this curve. So it would have been 2 minus 0 over N. What did N represent? The number of subintervals, which would be 8. So H is equal to 0.25 or 1/4, either one. Then y sub 0, y sub 1, y sub 2 is essentially the values that you would plug into the function as your output. I showed you guys how to do this using a table. The table was a way to keep everything nice and clean and organized using your calculator. I'm not going to write everything down. I'm just going to use my calculator to do this. Okay? So y'all remember the buttons I pressed?
Yes.
Stat enter.
Stat, enter, okay? And the keystroke history is showing up down here at the bottom. New computer, new program, so hopefully you ain't throwing nobody off. All right, what went into L1? The I values. The I values were essentially the breakup of your X region into those 8 subintervals starting at what value?
0,
0, going all the way up to what?
2.
Not 2.
8.
8. Because I had 8 subintervals. That I essentially represented in those sections. Okay. What went into L2?
Xi.
1/4 times L of 1.
1/4 times L1. What went into, and maybe I'll write it over here. So L1 was 0 to 8. L2, it was essentially your X sub i's. That comes from A plus I times H. A being the lower bound that you're trying to find the area of, H representing the value we got in blue, and then I, essentially those values from L1. So it would be 1/4 L1. I'm going to type it in exactly how I wrote it over there, but 1/4 second L1. If I do
Wait.
that, L2, all the values will show up. Yes, question.
So I thought like we couldn't go past, like we couldn't start before 0 and we couldn't go past 2. So I kind of like divided that by 8. So I had like 0 and then 0.25 and 0.5. So that's not how you do it.
No, that is how you do it. But do you see that right here? I have all those values that you were talking about. Oh, no, not for L1. Not for L1. The values that you got should technically go into L2. Again, using your calculator will give you all of these values. And plus, by finding that 0, that 1/4, that 1/2, that 3/4, what you are essentially finding is you're finding whatever this curve is from 0 to 2, you are finding essentially all those values. So yes, you do need 1/4, 1/2, 3/4, 1, and so on and so forth. If you're going to do it by hand, then yes, those are the values you want. But if you want the calculator to help you and assist you, you will need to type it in the way that I'm showing it in the green off to the right. If you do it by hand, then yes, you want to break it down that way, and then you won't even need a 0 to 8. But again, if you want to use your calculator, you'll use 0 to 8 for L1. And then those
Okay.
for L2.
Thank you.
Miss Anderson,
Yes,
is this supposed to be automatic like that?
if you type it into L1. So again, or sorry, not L1 and L2. So if you highlight L2 and then actually type in the function into L2, it will automatically populate that way. Then that way you won't have to plug in or do any additional math. Then what went into L3? The original function, but instead of putting in X, I'm going to put in L2, because all of my values that are my X's I'm plugging in are sitting in L2. So if I go up to L3, make sure L3 is highlighted, I'm going to type in my function, which was the square root of 4 minus X squared. But in this case, I'm going to do L2 squared. Then it's going to populate for me all the values that I need. Y sub 0 is 2. Y sub 1 is 1.9843. Y sub 2, 1.9365. Y sub 3, and so on and so forth. Those are the values that go into your formula. I'm gonna pause the video, write down these values for the video, then I'll press play. So now with everything plugged in, you just type it into your calculator and you get the approximate area underneath the curve with 8 subintervals using the trapezoidal rule to get what value?
Did I get a value? Yeah.
I got 3.089.
3.089. So then 3 significant figures will be 3.0,
9.
and that would be the area underneath the curve, approximately using 8 trapezoids. Of course, the more trapezoids you use, the more exact your area is going to be. That's what I said back in 5-7. Trapezoidal rule, the rectangular method, those are all ways to approximate the area. And at 5.8, we found how to find the antiderivative, which was one of the steps that we would need to find the exact area underneath the curve. Now we're tying all of this together to actually find the exact area underneath the curve. This is our last section of calculus. This is our last section that we need to learn material for A and I. And it is the Riemann integral, the fundamental theorem of calculus, and the definite integral. They all tie in together. So let's talk about each one of these individual pieces. Again, they all tie in together. The Riemann integral is exactly what you guys have been dealing with. That symbol, that integral symbol, that is called the Riemann integral, okay? Long time ago, a man named Riemann created this. So he is associated, that's his name, that's associated with that symbol, okay? Another way to represent the area underneath the curve, instead of doing the trapezoids, instead of doing the rectangles, is using the integral. So if you have a function where your y values are greater than 0 and x is in between 2 other values, a and b, as you can see in this picture, then to find the area underneath the curve, which is highlighted in pink and labeled area A, you take the integral from a to b of f of x. You take the integral from a to b of f of x dx. This is the way that you'll see these problems written. to find the exact area. It is read the integral of f of x from a to b with respect to x. This is also known as the definite integral. So if they say anything about Riemann's integral or the definite integral, realize they're the same thing. What I've boxed in blue. The integral of f of x from a to b with respect to x. So Riemann's integral or the definite integral allows you to find the area underneath a curve. If you notice the difference between the definite integral and the indefinite integral from the last section, definite integral has bounds on it. It has those values for a and b. Okay, that's one way you'll be able to tell the difference between the indefinite integral where you have to use your plus c versus your definite integral that actually allows you to find the exact area. What we're going to do is we're going to essentially find the exact area, but we're going to do it using what we know about area of different geometrical shapes. So the integral from 0 to 2 of 2x minus 1 dx. 2x, not minus 1, 2x plus 1. What does that look like graphically?
Should be a line.
It should be a line with a y-intercept where?
1,
At 1 and a slope of?
2.
Good job. Good thing. That gives me confirmation about the SAT part, because you know linear equations, not necessarily integrals, are on your SAT. How do I get points on the left side? Instead of going up 2 over 1 to the right,
Down to left 1.
down 2 left 1. Very good. Okay. So essentially what we have is we have this line. I'm going to cheat here. Like so. We are trying to find the area from 0 to 2. So essentially what we're looking for is this shape. What does this shape look like?
Trapezoid.
It's a trapezoid. Okay, I know it's kind of hard to see because it is small, but it is a trapezoid. Okay. Do y'all remember the area of a trapezoid, that formula?
Like times half or something.
Yep, you're in there, base 1 plus base 2. You multiply it by a half, but you also got to multiply it by something else. H, the height. Very good. So the bases of the trapezoid are this base right here. How long is this? 1. How long is this base? Again, 5. So my two bases are 1 and 5. What's my height? The height is the distance between the two bases. 2. So then the area underneath the curve from 0 to 2 of this function 2x plus 1 is going to be 6. Okay? It's going to be 6. Look at the next one. From 0 to 1 of the square root of 1 minus x squared. Anybody know what that looks like? If you're unsure, graph it. See what it looks like.
It looks like a mark at the top of x, and it starts at 1 and ends at, no, it starts at -1 and ends at 1.
So it looks like an arc, starts at 1, ends at -1, it goes up to 1, correct?
Yes.
Almost like a what? What does that look like? Huh? Let's
Hemisphere.
a semicircle. Hemisphere is 3-dimensional.
Oh.
But it looks like a semicircle, right? We're looking for the area underneath the curve from 0 to 1. So we're only looking for this. How much of the circle is that little piece? It's very little.
A quarter.
It's a quarter. So if I wanted to find the area underneath the curve from 0 to 1 of this function, I need the quarter of a circle formula. What's the formula for a circle? Wow. What's the formula for a circle? Area of a circle.
No clue.
2 pi r squared.
Not 2 pi r squared.
Pi r squared.
Pi r squared.
Sorry.
You gave me hope and then y'all took it away just that fast. All right, what's the radius of this circle?
1.
1. So then to find the area underneath the curve of this function, the square root of 1 minus x squared from 0 to 1, is going to be just pi over 4 or whatever that is as a decimal. You can find the area underneath the curve using Riemann's integral, using the definite integral and old school geometry formulas. As you can see here, trapezoid was created. It was a quarter of a circle, so we used the area of the circle formula, divided it by 4. Try this one on your own. Look at the bounds. If you need to, graph this so you can see what it looks like, and then find the area underneath the curve. What shape does this form?
Semicircle.
It forms a semicircle that starts where?
-2.
And ends at
-2.
in +2, right? The bounds. Okay, how high does it go?
2.
It goes up to 2, so it makes a semicircle. And so I'm looking for this entire area. So this is half of a circle. So to find the area of square root of 4 minus x squared from -2 to 2, I need half of the circle formula, which is what again? Pi r squared. What's the radius? 2. So 2 squared is?
4.
Half of 4 is?
2.
2 pi would be considered the exact area because it's not rounded. But if I did round this to 3 significant figures, what would it be?
6.28.
So then that would be the area underneath the curve. Using the definite integral, these particular functions do form geometric shapes. And so you can use your old school geometry formulas to find the area underneath the curve. The definite integral tells you from what value to another value, so you know exactly what you're looking at, what you're trying to find the area of. You could also do this using the integral when you don't know the equation, but you know the areas. Okay, you can use the same definite integral to find the area underneath the curve when you don't know the equations, but you know the areas. So for example, a positive function f of x from from 2 to 5 of a particular function, some function, the area is 10. And then from 5 to 9 on that same function, the area is 12. So essentially, you have some general function, right? And it's saying that from 2 to 5, the area underneath the curve from 2 to 5 is equal to 10. And then from 5 to 9, the area is equal to 12. Some function. I don't know what the function is, but I do know their areas. So if I'm asked to find the integral from 5 to 5 of f of x dx, what do you think it's going to be?
0.
It's going to be 0. Why do you say 0?
Because it's the same point.
It's the same point. I'm not going from like 5 to 9. I'm just at 5. So there's no area that's actually covered from 5 to 5. But what about from 2 to 9?
22.
How'd you get 22?
Add 10.
Because you add the area from 2 to 5 and then add the area from 5 to 9. 22. Very good. Try this one on your own. Try this one on your own. So in this particular problem, it says if the integral from 1 to 3 of some function is 2, and the integral from 1 to 6 of that same function is -3, you have to find the integral from 3 to 6 of that function. Now, before we actually do this, y'all notice that? It's -3. It's saying that area is a negative number. Area can be negative. If it is negative, what does that mean graphically?
It's under the x-axis.
It means that the curve is underneath or under the x-axis. Exactly. So if area is negative, that means at some point in time, the curve dips below the x-axis, and that's how we get a negative area. So just going to do a quick sketch here. So at some point it dips below like so. So from 1 to 3, the area is 2. From 1 to 6, so from 1 to 6, the area is -3. We're trying to figure out the area from 3 to 6.
-5.
Subtract the 2.
You would subtract the 2, and it would be -5. Okay? If you didn't see that, think of it like this. If I know the area from 1 to 6, and I know the area from 1 to 3, by subtracting them, I will actually get that area that's left over from 6, so from 3 to 6. The reason why we're able to draw these different conclusions is because just like with indefinite integrals, definite integrals have respective properties as well. There's a constant multiple rule with definite integrals, okay? There's a decomposition rule, which is what we applied in the last one. There's an addition rule. There's a zero rule. There's a negation rule. Get all these down. So again, you have these different rules. They're gonna, they can be used when you know the areas, don't know the equations, so on and so forth, okay? So like, here's another one. Suppose that from -1 to 1 of some function that we don't know, the area is -4, and it's asking you to determine the value of the integral from 1 to -1 of f of x dx. Well, if you look at what you're given, you see how the bounds that we were originally given are switched. We can use that negation rule from the other slide that essentially says you can flip the bounds and bring a negative on the outside. So that's what we want to do here. If I flip the bounds, now the negative's at the bottom, the positive's at the top. I pull a negative out, and I still have my function. Now what I can do is, since this looks exactly like my original given integral, all I need to do is plug in -4. And since I pulled out a negative using that negation rule, 2 negatives make a, so the area is +4.
Can you do that one more time?
So, since the bounds of what we were originally given are switched in this problem, we can switch them back by using the negation rule. And since we know that the integral from -1 to 1 of f of x dx is equal to -4, we can replace this entire expression with the -4.
Oh,
And since there's a negative on the outside, it just becomes positive. For this one, you see how there's a 2 in front of the function? We can use that constant multiple rule, which I think on the other slide was called like multiplication by constant. It's the constant multiple rule, which says that we can pull it out of the integral. And again, that's exactly what I was given. So I can replace that whole expression with the -4 and just bring down the 2. So then what's the area? -8. These rules also apply with other functions too. We're getting there. So find the part that I was looking forward to getting to. It is called the fundamental theorem of calculus. This is when you connect Riemann's integral, the definite integral, and differential calculus, which we did before we got into integration. You get the fundamental theorem of calculus. This formula, this theorem, allows you to calculate the area under curves when we are exactly. Before we were only able to estimate it using trapezoidal rule and rectangles. But this formula right here, the same formula that's also given to you in your reference booklet, I think, allows you to find the area underneath any curve. The exact area underneath any curve. Just a reminder, capital F means is the antiderivative of lowercase f. So essentially what we have to do is we have to find the antiderivative. Then we plug in the top bound in for all the x's. Then we plug the bottom bound into all the x's and we subtract the two. This is the fundamental theorem of calculus, and this is how we find the exact area underneath a curve. So, do you remember when we approximated the area from x equals 0 to x equals 1 of f of x equals x squared? That was the very first thing that you guys did with rectangles. 5-7. Okay, this was the slide. This was right here. We can use the fundamental theorem of calculus to actually find the exact area. Before we were just approximating it with lower rectangles and upper rectangles. And then depending on the number of rectangles we actually had, we could only approximate the area. Okay, remember I showed you this table right here. If I had about 10,000 rectangles, actually we'd probably get close to the exact area. Now we have a way of actually finding the exact area by taking the definite integral from 0 to 1 of x squared dx. All we have to do is take the antiderivative to start. What's the antiderivative of this function?
Then it will be 1/3 x cubed.
1/3 x to the third. With the definite integrals, we don't have to worry about the plus c. So that's the first thing we do. We find the antiderivative. Then we plug in our bounds. What I'm doing right here, this is nothing but like the notation to represent, we're going to plug in the bounds. It said capital F of B minus capital F of A. That means I plug in the top bound into the antiderivative, and I subtract it from when I plug in the bottom bound into the antiderivative. And that will give me my exact area every single time. The first term just becomes 1/3. Second term becomes 0. The area is 1/3. We found that by doing 10,000 rectangles originally. And even still, that was after we rounded. That is the exact area from 0 to 1 of x squared. We did the same thing with f of x equals x, okay? Remember, it was that linear function. Here it is. It was that linear function. It actually formed a triangle, so we used geometry formulas with it. We used rectangles with it, found the average. We can use the fundamental theorem of calculus now to find the exact area from 0 to 1 of the function. All I have to do is take the antiderivative, plug in the top bound, plug in the bottom bound, and subtract them. What's the antiderivative of x?
1/2 x squared.
Remember, no plus c when it's the definite integral. That's the one with the bounds. I'm going to evaluate it from 0 to 1, but I plug in the top bound first. Then I subtract it from when I plug in the bottom bound. So that's 1/2 1 squared minus 1/2 0 squared. First term is just 1/2. The second term is 0. The area is 1/2, and that's exactly what we found using geometric formulas. This is the exact way, using the fundamental theorem of calculus. All right. Here's some that are a little bit more involved, okay? The integral from 1 to 2 of x to the third minus 4x plus 5 dx. I attach the graph of both of these. Remember, when you do the definite integral, you're finding the area underneath the curve between those two x values and the x-axis. So essentially, this is what you're finding. That little bit of space, okay? Again, you find the antiderivative. You plug in the top bound, subtract it from when you plug in the bottom bound. When the functions get a little bit more involved, they become like more polynomial-like. You got to be careful. Don't lose any signs or anything anywhere. But you also have the luxury of using your calculator too, okay? So let's find the antiderivative. What's the antiderivative of x to the third?
1/4 x to the fourth power.
What's the antiderivative of negative 4x?
Negative 2x to the second power.
And the antiderivative of 5?
5x.
So first we find the antiderivative. Then we got to plug in our bounds. Which bound do I plug in first?
2,
2. Then I subtract it from when I plug in 1. So I'm going to write it out first. There's me plugging in the top bound. I'm going to subtract it from when I plug in the bottom bound. Now, this is what I was talking about being very careful. Make sure you subtract the entire value when you plug in 1. Include that additional set of parentheses so you know that whatever that is, when you plug in 1, you're subtracting that number. Not just the first term, but that number. So what I want you guys to do right now is I want you to actually type this into your calculator. Let's see if we can get the right number. So you get 11 over 4. That's the area from 1 to 2 of that function. Same thing over here. This time I'm going from 1 to 4. I'm looking for this area bounded between those two x values and the x-axis. I take the antiderivative. Plug in what number first? 4, and then 1. I'm going to rewrite this to help myself out. This becomes 3x to the what power? Negative 2. What's the antiderivative of 2x?
x squared.
X squared. What's the antiderivative of 3x to the negative second power? So now I have to evaluate the bounds. I plug in the top bound. Subtract it from when I plug in the lower bound. Make sure that you put parentheses around that second set so you know that you're subtracting that entire number right here. Let's see if you get it right. Yeah, so then this area would be 69 over 4. That's giving me confirmation that you guys are good with typing this in and we're not forgetting that additional set of parentheses. So what I want you guys to do is I want you to try these 3 on your own. What'd you guys get for A?
I got 7 over 2.
7 over 2?
I got 15 over 4.
15 over 4?
I got 15 over 4.
15 over 4.
Yes. So your antiderivative was 1/4 x to the 4th. You plug in which value first? 2. Subtract it from when you plug in 1. 2 to the 4th is 16. 16 divided by 4 is 4. Minus 1/4. So then it would be 3 3/4, which is 15 over 4. Good stuff. For B, somebody online, what'd you get?
I got -1 over 8.
I got the same thing.
All right, -1/8, good stuff. When you do the antiderivative, this would have given you a -1/8 x to the 8th. You plug in which bound first?
1.
1. Then you plug it in when you plug in 0. Even though this ends up being 0 for your second term, remember this, the antiderivative was a negative, 2 negatives make a positive. So this would have been -1/8 minus a -0, which turns to a +0. Good. We'll see. Anyone? See?
Oh, I think I got 11/108. I don't know if that's right.
11/108. Well, let's see. Remember, you need to make sure they're in the form of a power before you start taking the antiderivative. So move up those exponents or those variables to the numerator, making those exponents negative. What's the antiderivative of 4x to the -3rd power?
I got -2/x².
Yes. Because when you add 1, this ends up becoming a -2. So that'd be a -1/2, and it gets multiplied by 4. Then what about the 6x to the -4th power?
I got 2/x³.
Is it a +2/x³ or a -2/x³?
I got a +2 because there was already a negative there.
Exactly. This gives you x to the -3. That's going to be -1/3 that gets multiplied by 6, a -6. So it does become a positive. So then you evaluate it with the bounds. You plug in your upper bound. You subtract it from when you plug in your lower bound. Don't forget about that negative. Oops. Don't forget about the number either. Then when you type that in, you'll end up with, I don't know, -2/9 plus 2/27. Of course, you can do this in your calculator. Does that equate to be 11/108? Can I get confirmation? There we go. Yes, it's 11/108. And that is how you use the fundamental theorem of calculus to find the exact area. No more approximating. We can now use this formula to do this. Now, granted, if the problem does say use trapezoidal rule, you got to use it. Okay. And that is one of the concepts that you do need to know for this course. Whether they test that or they test the fundamental theorem of calculus, you need to know both. But remember, to do the fundamental theorem of calculus, you take the antiderivative. You plug in which bound first?
The upper one.
The top bound, the upper bound. Then you plug in the lower bound. And what do you do to those two values? You subtract them. That is the fundamental theorem of calculus. That is how you find the exact area underneath the curve. You can also apply this concept of the definite integral when you don't know the equation at all and you're given the areas. That's what we did earlier with those respective properties and rules. And you can also do them using geometric shapes. Okay, so if it just so happens the graph ends up being a trapezoid, a triangle, a circle, maybe even a square, you can find the area using old school geometry formulas. All these things are about finding the area underneath the curve. Okay, that's why they're bounds. This is known as the definite integral because now we're going from one x value to another x value. No plus c when you have the definite integral.